Alright, what's up again everybody? So, this is our sixth video, and this video we're talking about how to actually solve those equations of motions that we have been building up to this point. If you haven't watched the 5 videos before, again, depending if you need a refresher or not, I recommend you watch them. But from there, we developed equations of motions, and now, we've modeled that system, and now we need to solve that system. So, consider a 1 degree of freedom equation of motion like the one you see right here, and this is very typical. We've be in this model into our head because we've used it a lot in the last 5 videos, and you would have an expression like this. So now the scope of this video is that we're trying to solve to be able to understand is vibrational behavior, right? Now let's talk about a little bit about vibrational behavior. So vibration is an exchange of energy between kinetic and potential, right? So I'm either moving or I am displacing, but I'm constantly going back and forth between those energies. Think of a pendulum. I go up, I lose the kinetic, and I transform it all into potential, and then I get the potential again, and in the bottom I get it all into kinetic, and then I keep doing that. Another way to think about vibrations, or another way to put it, is that it is some oscillation, right, around a static equilibrium. Okay, so static equilibrium is a very important concept when we talk about vibrations, because it saves us tons of equation work. So let's talk here for a minute, right? So we have an equation, for example, we have an equation of motion for 1 degree of freedom system, like this. Okay, so we can come and say x is actually 2 factors, right? There is some static x plus some dynamic x, and the static x is the one, basically it's the x amount needed, the displacement that's needed for the system to get into some static equilibrium. For example, that mass, right, is going to be there, but the mass had to displace some x of s to react to the gravitational force that's on it. So that gravitational force is now in net equals 0, is in a static equilibrium with some deflection of the spring of excess and such. So that being said, this is important to know, because if we were to take this new data, we can just not worry about gravitational effects. Why? Because it's already lumped into the static equilibrium, and we are referencing our static equilibrium. So this is a very important concept, that we are referencing static equilibrium. Okay, so that being said, if I were to derive this, right, that term will go to 0 because it's a constant term. So I would get x d dot, and if I were to derive it again, x d double dot, right? Which tells me that in linear equations, I don't have to worry about anything but my spring, right, for the static equilibrium. Everything else shouldn't have some static equilibrium in it. Okay, now let's talk about how to solve the problem above. So obviously this is a linear differential equation, right? So that f of t does not have any contribution on the x. Therefore, I can safely bring that to 0 in order to solve that equation, because it's not going to affect me trying to find my natural frequencies and natural modes. Again, because it's not changing the nature of the system. Sorry, it could be affecting the natural modes, but it's not affecting the natural frequency of the system. Okay, so let's talk here about solving this equation. So I'm going to skip to the end, and then I'm going to talk about a possible solution. So just as a hint, you have 4 possible solutions to this, right? You have some magnitude multiplied by sine of omega t, some amplitude multiplied by cosine of omega t, some amplitude multiplied by cosine of omega t plus phi, which is my phase, or my ultimate favorite, and you might know why if you've taken Laplace transformations, but a magnitude I omega t, exponential of I omega t. Looks very similar, right? To usually when you solve in Laplace, you get E S of t, right? All right, so let us attempt to solve this equation right here, and let us talk about how we can solve it and what information do we get out of solving it. Before we go there, I just want to talk about a couple of key elements that we need to define for definition purposes before we move forward. So let's say I have some wave here, okay? So this here is my x naught, and this here is my amplitude, right? Because think about it, my highest here is when that sine omega t is equal to 1, so it's going to be a1. My highest here is that when it's equal to 1, so a1, and such. So this is my amplitude, and between this amplitude and this other amplitude, the next amplitude, which is your 2 pi, the full cycle, the 360 degree one phase, or 180, right, switch, you get, why is this confusing me, 360, you get the period. Okay, so the period is between, like, basically it's a one full cycle, right? Okay, so we have some time here that we need to talk about, which is, if I were to call this t, I would call this time here delta t. And if this is omega times t, right, then I would call this here phi. And this is important because in many times this can be known as the delay, and you can actually calculate that by phi times omega, phi equal to omega delta t. As you can see, I multiplied t by omega and it gave me phi. So this is my phase angle. So this is the delay, if you will, of the response that I'm getting, okay, between what I first got and the actual peak. Okay, so that being said, now that we define this, right, we're gonna come back to that graph because there's a couple of key elements that we want to discuss on this graph. But also, right, one element here real quick I want to talk about is that t, the period, right, omega n, you would expect omega n to be 1 over t, right? Right? I'm not going to speak about like wavelength and frequency, but you would expect omega n, like if you've ever taken like any light related courses, but you would expect the frequency of happening is equal to your natural frequency is equal to 1 over the period, or the time it's taken for a full cycle. Okay, again, very intuitive stuff, very easy, just stuff that it's very important to define before we dig deeper into understanding what's happening or solving the equation. Again, we'll come back to that graph because there's cool tricks that we need to know about that graph. All right, so again, remember our equation, which is mx dot plus cx dot plus kx equal to 0, right? We said that the force doesn't affect us as much, doesn't affect the natural frequencies, so it's safe for us when we try to solve this to bring it to 0. That being said, we can plug in a solution, right, to the differential equation, which is a to the exponential of st, right? So you have your x dot here is equal to sa est, and your x double dot is equal to s squared aest, right? So let's take that and plug it back in. You can already see that I have like some trolling that's the beauty about the exponential when it comes to integrating it and such, is that you can see that this term keeps surviving. So I can just put that term out. So I can say AE to the ST, and then in here, I would have the S squared left. So S squared M, or it's better to write as MS squared plus CS plus K equal to 0. Okay, so let's discuss which of those terms can equal 0. This term here can't equal to 0, right? This term here, if it's equal to 0, then we don't have vibrations. Then this is a trivial problem. So why are we even, discussing this? So it's not an interested problem if this is equal to 0. Like, we're not interested in that problem. This term here has to equal 0. So now we get that the term mx squared plus CS plus K equal to 0. Now, the roots of this can be written right away as minus b over, positive square root of b squared minus 4ac, which is m times k, over 2a, right? Okay. Now remember that if I'm trying to find the natural frequency, so let's say my mx squared plus cx dot plus kx equal to 0. If I'm trying to find the natural frequency here, not this term, because that's the term before I solve it. This is a term after I solve it. So if I were to write this again, ms squared plus cs plus k equal to 0, if I were to come here and say, okay, I do not have any, I assume that my damping is equal to 0 because it doesn't affect omega n, and we'll talk about that later, or it affects it but in a very, very, very small percentage. We'll talk about that. So if I were to say, let's kill that term, right, I would get that my solution, which is omega n squared, is equal to k over m, right? So this is, we already know that term, right? The natural frequency term. You might think, oh, this is a positive, this is not a negative. So how is this turning around to be positive? Because, if we are talking omega n, you have to take the force out in this direction, the k will be in the other direction, so it will be negative. I just overly simplified it. So knowing that this term is equal to that, I can go ahead and rewrite this equation in a different way. So I can write my roots as negative zeta omega n, I believe, positive or negative omega n square root of zeta squared minus 1. Okay? This term here is often referred to as alpha, and this term here is often referred to as omega d. Again, we'll talk more about that here in a second. So, that being said, we've reached the roots of the equation, right? So now I know my frequencies, right? Omega d is my natural frequency damped, right, of the system. And by deduction, I know that now my zeta is equal to C over 2 omega mk, right? And that term is often referred to as critical damping, right? So this is a very important aspect of what we're talking about today in terms of solving equations of motions for vibrations. So technically, right now, we solved it, because what we can do now is that we can take our roots here right, and plug it in, and we can get a value for A. Now, I'm not going to do that because, again, just you have to take the roots, plug it in with initial conditions, because that's where it's going to matter. Initial conditions are needed to define your modes, hence the A's, to get modes, and the modes, I mean, like, you know, the A's. All right. Well, we've talked about this term here, the omega n. So this omega d is equal to omega n square root of zeta squared minus 1. Now this here has a phase problem, so when you put in the I, right, in there, because technically that root is complex, right? So when you put in that I, you get omega d is equal to omega n 1 minus zeta squared. Okay? All right. So we have multiple situations for zeta here. So let's discuss each of them. Okay? So if my zeta is equal to 0, right? If I put it in here, then I get d is equal to omega n, because there is no damping in the system, which means that my system is free, which means this one, you know, this holds true. Okay, so let's discuss this property, right? If my zeta is bigger than 1, if I have damping that's more than my critical damping of the system. So if I have more than 1 here, right, this here will be negative. If this is negative, then I basically go into the complex, which means it's not real anymore, which means I get this type of situation, right, where it dies out quickly. And this is called over-damped. And over-damped is very known for having nothing for us to solve for. So, you know, we're not interested in over-damped systems because they're systems that have no oscillation whatsoever, right? Now, critically damped. Okay, so critically damped, we're talking about, so here we have no omega d or omega n. We don't have that because they're imaginary. All right, so critically damped. So let's go here and put zeta equal to 1. So we have 1 minus 1, that's a 0 inside, which means I actually don't have. So my omega n is equal to 0, which means, right, my system is getting the behavior and dying out right away. This system is just dying right away. This system is getting the behavior and just dying out of it, no oscillation whatsoever. This is called critically damped. Mainly the name is critically damped because your C is going to equal to your C critical, right? Which is what we've talked about before for a 1 degree of freedom system. All right, so let's consider a situation where we have zeta less than 1. So if we have zeta less than 1 here, right, then this is positive, then we get omega d as a function of omega n. Okay, so this is great. So let us come and say, okay, I have ranges. I have ranges from 0.01, all right, which is a system that's barely damped, to 0.99, which is a system that's, you know, basically damped to the teeth, right, under the critical damp, right? So I think this is really good to talk about this because it helps us understand the effect of damping on our system or on our natural frequencies, right? So I'm gonna have my calculator here on my iPhone. Hopefully it doesn't die on me. And I am going to say 0.01 times 0.01, right? Which gives me, so this here is gonna give me omega n, like basically omega d is equal to omega n times 1 minus 0.0001, which is basically 1. So we're getting is equal to omega n, right? So barely. Okay, so this is my low bound. Let's talk about the high bound. So 0.99 times 0.99, right? So that gives me 0.9801. Okay, so 1 minus that, omega n, omega d, right? So 1 minus 0.9801, right? So this inside of here is 0.0199. When you square root that, and then square root on my 199, 0.0199 square root, we get is equal to 0.14 of the omega n. Let me just check my math here real quick. 0.99 times. Yep. That means that if I am critically, like if I'm just a tad bit of being critically damped, right? I'm 15%, or roughly I'm 15%, like omega d is equal to 15% omega n. Okay? Now, why is this important here? Why am I talking about this? Because I want to talk to you about the effect of damping. I want to talk to you about how damping does not have a huge effect on your system. I mean, yes, it does have some effect on your system, but it doesn't have a huge effect on your system. So you can actually, for the most part, you can actually deal with your damping. You know, assume omega n's, and then, you know, you can see like 10% of change or something like that. That will be your omega n. Okay, like that, you know, up to 10%. If you have done much, like we can actually dig more into it, but I'm gonna spare you the math. But basically, changes in zeta doesn't account for huge changes. Oh, this is bad. For huge changes in omega n. Okay? All right. So that being said, we've established our omega d about omega n. So we typically, right, we're going to talk about this more in our next video. But the a's here, right, and solving for those a's are going to be our mode shapes. And then solving for our omega n's is going to be our natural frequencies. So we're going to talk a little bit here about isolation techniques, and about if you have a problem with a vibration problem with the system, the solution is not to throw damping on it, because you're not really moving the natural frequency by that much. The solution is to isolate it, to move the frequency away from the natural frequency. I'll be showing you a graph later, which we're going to be talking about the transfer functions. Actually, I'm going to go here. The transfer functions, you know, basically we're going to be talking about transmissibility, right? And how, you know, if I say I have some F, you know, that affects our displacement, right? I can come say, okay, so this here is actually dependent on omega over omega n. So if I were to actually design this, if I were to know what I'm shooting for here and design that by manipulating mainly, two things, by manipulating the stiffness and by manipulating the mass. We'll talk more about this, and yeah, we'll discuss that more. Thank you for watching, and see you next time. We're going into pretty interesting stuff here.